So I'm going to start off our mathematical discussion of dimensionality reduction by talking about principal components, which will be the main building block for the techniques that we're going to talk about in this unit. So let me just set up the problem with some definitions. We have some n records of data, and each record will denote by the vector xi, and will have p features. So we can, as normal, represent that as a matrix with n samples and p features across the columns. Now, it's important to recognize here, at this point, it's a completely unsupervised learning problem. We don't have any targets associated with the y for now. We just have the vectors x that we want to perform dimensionality reduction on. Now, the reason why we would want to do dimensionality reduction is whenever the number of features p is large, and somehow we want to transform that into some vectors with some kind of smaller number of features or dimensions. So that's what we mean by dimensionality reduction. Okay, the key idea that we want to use for dimensionality reduction, at least in this unit, is something called projections, which you may have seen in any linear algebra class. And for us in machine learning, or at least in PCA, what we do to reduce the dimension in essence is to project that high dimensional vector onto a lower dimensional space. So let me just walk through the definitions of what we mean by projections. So if you've taken linear algebra, you may remember that if you have vectors z and v, the projection of that z onto v is just given by this formula. So that is, we take the vector z and we align it on the vector v with some coefficient alpha, which is given by this ratio of inner products. And that can be sort of mathematically or visually seen like this. We have a vector z, and we're projecting that down to this vector z hat aligned with v. And a kind of standard result in linear algebra, and it's not hard to show this, is that actually this projection is the closest point to z that's aligned along this subspace spanned by v. So that's just what it is mathematically, or visually. Now, the idea in principal component analysis comes from trying to maximize what you would call the directional variance. So let me describe it like this. We have our n data records, and let's say I think about some candidate direction, v. And just for, without loss of generality, we can say that that direction is unit magnitude. Right? Now, in this case, let zi be the coefficient of xi projected onto v. So here's our ith data record, and in this case, zi is the length of that projection onto this vector v. And we could then take the sample mean of this coefficient, let's call it z bar, so that's the average value, and then we'll call sz squared is the sample variance. So for each record, I get a different zi. Sometimes I would project it here, sometimes I'll project it to land somewhere else along this line, and then I take the mean and variance of that coefficient. Now, the idea of principal component analysis is that we want to find the direction v that maximizes this variance along this. Now, you might ask why you want to do that. The idea is that somehow if we can find this vector that maximizes this variance, I'm somehow capturing most of the variation of the data. So if I can find vectors which do this, hopefully by projecting our data onto this set of vectors, we won't lose much information. We're going to make this concept more precise in the next section, but let's go ahead now and try to figure out how we can find a vector v that maximizes this variance. So to do this, we have to just review some couple more linear algebra points, and one is called a sample covariance matrix. So remember that you have the sample mean of the data is just found by taking the average of all the data records. Or in terms of that matrix, we'd be finding the average along each column. Now the sample covariance matrix is a P by P matrix with this formula here. And it basically tells you it's really the sample covariance of the ith feature, the kth and lth feature in the data averaged over the data records I. So if you have two features, let's say they are the price of the house and the square footage of the house, this would be the sample covariance between those features, and you construct the matrix of all of those features. You can also write this in vector form like this. This product here is none other than this outer product between xi minus x bar and xi minus x bar transpose. And then when you do this, you can show, and I'm not going to show it here, that this is equivalent to writing it as a matrix product of what I will call x tilde transpose and x tilde, where x tilde is just the data matrix with the samples removed. So I'll let you show this on your own. It's not that hard of a calculation. So let me show you now how we can use the sample mean and covariance to compute the directional variance. So again, Zi is going to denote the coefficient of the projection of our ith data record onto a potential vector v, which is just the inner product of v and xi. And I want to show that I can compute the sample mean and variance of Zi from the data mean and data covariance. So let's start with the sample mean. So sample mean, Z bar, is just the mean of these. But if I can first substitute V transpose Xi here, I pull that V transpose out, and this quantity in this bracket here is none other than our data sample mean. So Z bar is just V transpose the data sample mean. Sample variance is a little harder to show, but it's not that bad. Remember, our sample variance is just because Zi is a scalar, is just going to be the average of Zi minus its mean Z bar. But I can substitute V transpose Xi for Zi and V transpose X bar and get this. But this value squared is just this times this, because of course A transpose B is B transpose A for any real vector. And then I can pull out these V's, and in this middle I get this Q. So our directional variance is just this inner product of V transpose times the sample covariance times V. Okay, so with those definitions, I want to show you how we can maximize the directional variance. So again, if we have a vector V from the previous slide, the directional variance along that direction is none other than V transpose QV, where Q is our sample covariance matrix. And if we want to maximize that quantity, and we're going to do that subject to the vector having a unit norm. So this is a constrained optimization problem. And to describe its solution, let's recall something called eigenvalues and eigenvectors, which you hopefully saw in linear algebra. So because Q is a symmetric matrix, and it's P by P, it will have P eigenvectors. And an eigenvector just means that when you go Q times Vj, you get back Vj with some scaling lambda j. And those values lambda j are called the eigenvalues. And in this case, you can show that the eigenvalues are always real and non-negative. And we'll just sort them with lambda 1 being the largest eigenvalue. Okay, with that, our solution is the following, that you can show that any local maxima of this constrained optimization is always just an eigenvector. And in fact, the highest value will go to the highest eigenvector, and the second highest value will go to the second highest vector, and so on. So I'll show this below. It's just some simple constraint optimization. But let me try to use this to talk about principal components. So the principal components given this definition are just none other than the eigenvectors of the sample covariance matrix. And we're just always going to normalize them, and we'll sort them from the largest eigenvector to the smallest eigenvector. And each vector will have the same dimension as the data. Now, you can always, in this case, you can always show that the eigenvectors will always be orthogonal, and that's a property of this being a covariance matrix. I'm not going to show that, but it's not that hard. But what I want to show you here is how to interpret them geometrically in the data. So that first eigenvector, which will be called the first principal component, really represents the direction of maximum variance. And that second eigenvector is the direction with the second most variance, and so on. So here's a picture which I just took from the internet. You have some data points just with the blue dots. And this green line here is the line along the first principal component dimension. And what you can see here is kind of the direction that captures most of the variation of the data. And then the second direction is always orthogonal, and in this case captures less dimension. This is a two-dimensional data set, so there would be two PC dimensions. And if it was three-dimensional, you would have three dimensions, and so on. So let me just do this quick proof of this fact that I said before, that the PCs are the eigenvectors. So remember that the PCs are the solutions to this constraint optimization problem. We're trying to maximize V transpose QV subject to its norm being 1. Whenever you have a constrained optimization problem, and you might have recalled this from the end of our unit on SVMs, is that we define something called the Lagrangian. And the Lagrangian is a cost function which has the original objective, called the primal objective, and then it has a second term with the constraint, and the constraint is multiplied by lambda. In this case, I replace that constraint v equal to 1 with the norm of v squared equal to 1, because they're the same. And so I then multiply that by lambda. And then, if you recall from constrained optimization, that any local solution to this has to satisfy the property that the derivative of the Lagrangian with respect to v is equal to 0. So just like in unconstrained optimization, you take the derivative of the objective function. In constrained optimization, you take the derivative of the Lagrangian. And I'm not going to show it here, but it's pretty easy to show that the derivative of v transpose qv is just 2 times qv. And the derivative of this norm v squared is 2v. So if you put that in here, set it equal to 0, you get qv equals lambda v. And that means that v is just an eigenvector of q. So that's how we show that. So that wraps up, or at least our definitions of principal components. Before we go on any further, I want you to go back to the GitHub site and try this very simple exercise on this kind of made up data. I just want you to manually compute the principal components and just do a few simple exercises just to illustrate the projections of the data onto those principal components. Once you do that, I think you'll be in good shape for us to next talk about principal component analysis.